Hello students, welcome back. Let's resume our discussion in section 2. We just went through the rank theorem. We stated and proved. And there, the dimension of the image is called the rank of a linear map. And the rank of a matrix is the same as the rank of the linear map associated to the original matrix. And one good way to visualize that is through these. So how is the linear map associated to the matrix? I think I said backward, excuse me. How is the matrix associated to the linear map defined? We have basis vectors v1, v2, and so on and so forth, all the way up to vn, with respect to the basis w1, w2 to wm. Will have the coordinate expressions. So the image vector of v1 and express the coordinate vectors as column, and image vector L of v2 express it as a column, and finally the image vector L of vn and express its coordinate vector as a column with respect to the basis w1, w2 all the way to wm, and that is the basis vector. That is the matrix associated to this linear map, basically. So it's y1. I have to use superscript because these are column vectors. So that's what this matrix is. Now, L of v1, L of v2, all the way up to L of vn, they generate the image. You see, in theorem 1.4, we saw those. The image vectors of the basis vectors generate the image. Okay? So image space is generated by those L of v1, L of v2, all the way over to L of vn. And then the dimension of the image is nothing more than the rank here by that. And that thing is called the column rank because all these vectors are column vectors. So consequently, the column rank is equal to the dimension of the linear map associated to the original matrix. So whether you look at it in linear map's point of view or the matrix point of view, you get the same concept, the rank. And the proof that column rank and row ranks are the same, that's a bit tricky because we have to do some tedious elementary row and column operations. But we can actually prove that column rank and row rank are the same. The detail is left to students, yes, but I doubt anybody would actually take time actually going through that. It's elementary, yes, but it's too tedious. Just remember the result. Whether you do this through rows or columns, the rank remains the same, and the same rank is actually this rank, the rank of the linear map associated to it. The next topic is an optional topic, change of basis. According to our textbook author, this topic is buried in the appendix. So what I'm going to say from this point on is just optional topic. So you can skip this video. As a matter of fact, it's okay skip entire video after the rank theorem. Okay, what I'm trying to say is this. What if we have two different bases of the same vector space so that the same linear map can be expressed as two different matrices? How are those two matrices are related? And that's what we are trying to establish here. And the proof is, let's say, both tricky and difficult, but the end result is not that tricky. The end result is this. Here we go. Matrix B and matrix A are called similar if there is a invertible matrix T so that you can express B as T inverse AT. In that case, we say A and B are similar, and it'll turn out that that's how two matrices that represent the same linear map with respect to different bases are related. So if we have similarity between matrices A and B, then that means A and B represent the same linear map, or A and B are associated to the same linear map, but with respect to different bases. And then there are some algebra of similar matrices. Let's see. Okay, algebra of similar matrices. A and B are similar, then A to the nth power and B to the nth power are also similar, and it's not too difficult to prove. A and B are similar means B is T inverse AT, and if I simply take the nth iteration, then it's a matrix multiplication where we have a bunch of T times T inverse canceling each other into I, and a T times T inverse over and over again, and then all these disappear. And then what do you get? First T inverse and last T stays, and all T inverse in the middle just all cancel out, and in the end, what do we have? We have T inverse A to the nth power T. So if A and B are similar, then B to the nth power and A to the nth power are similar as well. The polynomial expression of A and the same polynomial expression of B are similar as well. And that's because, you see, let's see. Okay, all right. P of B is this one. And then that's the same as, and then this is T inverse A T, and then this is T inverse A and to the nth power T and so on. And then as far as this I is concerned, you can write like this, because identity matrix is commutative to everything. You see, B to the nth power is this, n minus first power is that, and so on and so forth. And then if I take T inverse and T all the way outside, and then t all the way outside, then that's basically throwing away all the t's and t inverses in the intermediate part. And thus, this is the same as polynomial expression of A. Oops. No. T inverse. Okay, like that. So yes, polynomial expressions are similar as well. So establishing the similarity, that part is difficult, and then we're going to do that in a separate video. But working with similarity is not too difficult. Okay, and that was for polynomial, and this is for power series. Even if we go infinite series, in that case we have to worry about the convergence, but the convergence issue is analytic. So if that appears, a convergence problem becomes an issue in analysis, that's a different story. Here in linear algebra, let's not worry too much about the convergence. Let's assume convergence is okay. And absolute convergence and everything so that we can change the order of addition and things like those. Assume all that. And if you apply the exactly the same logic as polynomial as before, then you can prove that two power series are similar as well. The detail is left to the students. Okay. And then another thing. Oh, okay. Assume A and B are similar, all right? If A is invertible, then B is also invertible. Not only that, A inverse and B inverse are similar to each other. How do we prove that? I do not want to show this to you because I think this is a very, very good homework problem set. So, okay, I'm not gonna show you this proof here. Instead, let me give you a hint. Let me give you a hint instead. No proof, just hint. So, if you want to prove that B is invertible, then one way to prove it is something times B is equal to I. So if you have this, if you have a candidate of inverse, so that something times B is equal to I, then you're through. Okay? And now, what do we know? This is what you know. A inverse exists, so A inverse times A is equal to I. That's what we know. And B is equal to T inverse A T. Using these two, your job is to figure out a way to get something times B is equal to I. Can you work it out? Do you need more help? Okay. Just one more hint then. So instead of B is equal to T inverse AT, I can flip these T's to the other side. T B T inverse is equal to A. So here you can multiply T to both left hand and right hand side. So kill this one off. T inverse to both right hand side here and there to kill this one off. How to get from here to there is left to the students. Now you can use this and that so that you end up this. Okay, I'll stop here. Okay, let's recap. We're going to do this in separate video, too complicated. Let's see. If you have a linear map from one vector space to another with set basis, then that linear map is associated to a matrix, n by n matrix. Now, if you have different basis system for both vector spaces V and W, then you're going to get different matrix associated to the same linear map. The question here is, how are those two matrices associated? How are those two matrices related to each other? The conclusion turns out to be those two matrices are related like this. B is equal to T inverse AT, where this matrix T is called the transition matrix. And once you have this kind of relation, if certain invertible matrix T can be found, then we say A and B are similar. And A and B are similar, that means they're associated with the same linear map, so they must share a lot of properties. And some of those properties are here. A and B are similar, then A to the nth power and B to the nth power are similar, and we proved it. A polynomial expression of A and polynomial expression of B are similar, we proved that too. A power series expression of A and power series expression of B are similar as well. And we didn't go through all the details, but I'll leave the details to the students. And finally, if one is invertible, the other is invertible as well. And moreover, the inverse matrices are similar as well. And that one, I'd really like to leave it as a homework because it's really a good problem. It really combines the similarity things and also the conditions in regards to invertibility. So I didn't give you the full proof. I gave you some hint and then stopped. So much for the elementary part of change of basis. The technical part is left to a separate video. Thanks.